Hi, everybody. It's Professor Mitchell. We're going to try this today without my talking head in the corner because Wi-Fi seems to be very busy today and I keep getting kicked off when I've been trying to record this. So I'm hoping this will help. Today we're talking about section 8.3, testing a claim about a population mean. Testing a claim about a population mean is one of the most important methods presented in this book and in this course. Part one of this section deals with the very realistic and commonly used case in which the population standard deviation sigma is not known. You may remember back in chapter 7 when we talked about finding confidence interval estimates for a population mean, we also concentrated on the case where the population standard deviation is not known. Part 2 includes a brief discussion of the procedure used when sigma is known, which is very rare. So the objective in this section is to use a formal hypothesis test to test a claim about a population mean mu. To review the notation we'll be using, n is the size of the sample, x bar is the sample mean, S is the sample standard deviation, and we will use mu sub x bar or possibly just mu for the population mean. Remember, for mu sub x bar, which is the mean of the sampling distribution, is equal to the population mean. So you can use either one of these. The requirements for this type of hypothesis test: number one, the sample is a simple random sample, and either the original population is normally distributed or the sample size is larger than 30. This is the test statistic that we'll be using in the case when the population standard deviation is not known. So this is from the student's t-distribution that we looked at in the last chapter. And this test statistic is t equals x bar minus the population mean mu, or mu sub x bar, divided by s over the square root of n. And we will continue to use the two different approaches that we talked about in the last section. Either we'll use the p-value approach. Now, what's going to be new in this section is to find an exact p-value, you actually have to use technology. If you use table A3, the best you can do is get a range of values for your p-value, which is often usually good enough. Or we'll use the critical value approach, which also uses table A3. So the requirement of normality, or that n is greater than 30. If the original population is not normally distributed, then the sample size has to be bigger than 30 in order to use this process. Sample sizes of 15 to 30 are sufficient if the population has a distribution that is not far from normal. We skipped a section, I believe it was in chapter 6, on assessing normality. So we will concentrate on problems where either the original population is normally distributed or the samples are larger than 30. Reviewing some properties of the student t-distribution. Number one, it's different for different sample sizes. That's why we need to have the degrees of freedom. Number two, the student t-distribution has the same general bell shape as the standard normal distribution. It does have greater variability because we're using S to estimate sigma. Number three, the student t-distribution has a mean of t equals 0. Number four, the standard deviation of the student t-distribution varies with the sample size and is greater than 1. And number five, as the sample size n gets larger, the student t-distribution gets closer to the standard normal distribution. So our first example, the author of your textbook obtained times of sleep for randomly selected adult subjects included in the National Health and Nutrition Examination Study, and those times in hours are listed below. Here are the unrounded statistics for this sample. N equals 12, X bar equals 6.83333 hours, and the sample standard deviation is about 1.9924 hours. A common recommendation is that adults should sleep between 7 and 9 hours each night. We're going to use the p-value method with a 0.05 significance level to test the claim that the mean amount of sleep for adults is less than 7 hours. Now notice they've given me the actual sample data. However, they were also nice enough to provide the sample statistics, so we won't need we won't need to do anything with this sample data. So first, let's check our requirements. First, the sample is a simple random sample. Second, we need to check that either the population is normally distributed or the sample size is bigger than 30. This sample size is only 12, so we would need our population to be normally distributed. And this is where we get into the assessing normality that we did not cover. So I'll just put this up here for a brief second, give you a little idea of what that looks like. But again, this is not something you're going to have to worry about if you're taking my class. All right, so let's go ahead and do our hypothesis test. First step, the claim that the mean amount of 11 hours becomes mu is less than 7. Step 2, the opposite of that statement would be that mu is greater than or equal to 7 hours. Not contain equality, but becomes the alternative hypothesis. So that would be mu is less than 7. And our null hypothesis is going to be that mu equals 7. All right, in step 4, we note that they asked us to use a significance level of 0.05. In step 5, because the claim is made about the population mean, the sample statistic most relevant to this test is the sample mean. Using our formula down here, we find that the calculated test statistic is negative 0.290. Notice that they plugged unrounded sample statistics into this formula. And it's generally a good idea to round as little as possible until you get to the end of the problem. It gives you more accurate results. All right, so here are some different technologies that can be used to find the p-value. I'm going to use a different one. I'm going to use StatTrak. So let me pull up StatTrak. What I have open here is a Google page where I've typed in t-distribution calculator. The first result is StatTrak, so I'm going to click on that. Okay, here we go. So the random variable is the t-score. The degrees of freedom, because my sample size is 12, that means the degrees of freedom is 11. And the t-score is negative 0.290. You can see that there from the last time I tried this. Now, before I hit calculate, I want to draw you a little picture of what this value actually represents. So here is my t-distribution with 0 right in the middle. So negative 0.290 would be off here to the left. I think I'll just put a t here, but that does represent negative 0.290. The p-value represents the probability that in a world where the population mean really is 7, that I would get a sample at least as extreme as the one I found. Now, in this case, at least as extreme means at least as low as, because this is a left-tailed test. The reason I know it's a left-tailed test is because the alternative hypothesis is mu is less than 7. So the p-value is going to represent the area to the left of negative 0.290. I think I will put that right there. All right, so I hit calculate. And eventually it should tell me that the p-value is, okay, there's the p-value. As I mentioned, my internet is a little slow today. The p-value is 0.3886. All right, so again, what that means is that if the population mean really was 7, the probability of getting a sample this low, at least this low, is 0.3887. That is not strong evidence at all that the null hypothesis is false. So in this case, we're going to fail to reject the null hypothesis. And hopefully you remember in a previous section, I mentioned the little rhyme that might help you remember this. If p is low, the null must go. If p is high, the null will fly, as in it's acceptable, okay? Because the p-value is greater than the significance level, we fail to reject the null hypothesis. And what that means is we conclude there is not sufficient evidence to support the claim that the mean amount of adult sleep is less than 7 hours. If suitable technology is not available to find the p-value, you can use table A3, but again, this is only to identify a range of values containing the p-value. In using table A3, keep in mind that it is designed for positive values of t and right tail areas only. So in the case of a left tail test, you have to use the fact that the t distribution is symmetric. So let me switch over. Well, first of all, let me switch over to table A3, but then I want to draw you a picture of what this means. So if we go down to 11 degrees of freedom, what I'm looking for is the t-value that is closest to 0.290. Remember, this is we only have positive t-values in this table. In that row, which is 1.363. So now I want to switch over to my pad so I can explain what this means. Okay. So here is my t distribution. And we have a calculated test statistic, negative 0.290. Our p-value is the area to the left of that value, okay? But again, because table A3 only has positive t-values and right tail areas, I'm going to use symmetry to instead talk about the area to the right of positive 0.290. So when I looked in the table, the closest t-value that I found to 0.290 was 1.363. And according to the table, the area to the right of 1.363 is 0.10. Since this area all the way from here on up represents my p-value, that p-value has to be greater than 0.10. Okay. So this is good enough for what we're trying to do because we just want to compare our p-value to alpha, the level of significance. So what I would say is, since my p-value is greater than 0.10, which is greater than 0.05, and that's my alpha value, I could still say fail to reject the null hypothesis. Okay, so the disadvantage is that it doesn't give me an exact p-value, but it gives me a range that's good enough for what I'm trying to do. All I want to know is it bigger than or less than 0.05? All right, so switching back to PowerPoint. Okay. So this is going to say the same thing as what I just showed you. Using the test statistic of t equals negative 0.290 with table A3, examine the values of t in the row for degrees of freedom equals 11 to see that 0.290 is less than all the listed t values in the row. That indicates that the area in the left tail below negative 0.290, again, that's by symmetry, is greater than 0.10. So in this case, table A3 allows us to conclude that the p-value is greater than 0.1. Technology gave us the specific p-value. Either way, we get the same conclusion, fail to reject the null hypothesis. Example 1 is a left tail test with test statistic t equals negative 0.290. The sample size is n equals 12. The degrees of freedom is 11. So now we're going to talk about how would this look using the critical value approach. So what we're going to do, let's see, I think I will first switch over to my pad. Okay, so the critical value in this problem, we want to know what is the value of t that cuts off the bottom 5% of the student's t distribution. Okay, so in order to figure that out, we are going to go back to table A3. We're going to go to degrees of freedom equals 11, and then we're going to go to the column that says area in one tail 0.05. And where that row and that column meet, I see a 1.796. And what that means is that this t-value right here is negative 1.796. Okay, so this region over here is called a critical region, or sometimes a rejection region. If my calculated test statistic, sorry about that, I was thinking about something else. If my calculated test statistic comes out to be less than or equal to negative 1.796, then I'm going to reject my null hypothesis. However, we already know that our calculated test statistic came out to negative 0.290. Because that value does not fall within the critical region, again, my conclusion would be fail to reject the null hypothesis. Okay, so switching back to the PowerPoint. Here we go. All right, so you just saw everything that it says on here. And there's their picture. The figure shows that the test statistic of t equals negative 0.290 does not fall within the critical region bounded by the critical value t equals negative 1.796. So again, that would be fail to reject the null hypothesis. Same conclusion as what we got before. All right, a little bit about the confidence interval approach. In the first section, we talked about how the confidence interval approach for population mean is equivalent to either the p-value approach or the critical value approach. In other words, it will always give you the same conclusion. So the first example that we just went over is a left-tailed test with significance level 0.05. So we should use 90% as the confidence level. I remember we had an example like this in section 8.2. The reason that the confidence level becomes 90% is because if the area in one in the middle. Okay. So for the sample data given in the first example, the 90% confidence interval estimate of mu is between 5.8 and 7.87 hours. All right, why don't we see how they got that confidence interval? So remember, the confidence interval for a population mean is mu plus or minus the error bound. And in the case of population mean with standard deviation unknown, the error bound is t sub alpha over 2 times s over the square root of n. So in this case, t sub alpha over 2 will be that same 1.796 that we were just looking at in the table. The sample standard deviation was about 1.9924, and the sample size is 12. So when I crunch those numbers, I get that the error bound is 1.033. Oops, I'm sorry, I made a mistake up here. This should be x bar. X bar plus or minus the error bound. There we go. Okay. All right, so x bar then plus or minus the error bound. X bar was, let's see, I was just looking at it here a second ago. .83, I believe. Yeah, about 6.833. And when I add and subtract my error bound 1.033, I get as my lower bound 5.80, and I get as my upper bound 7.866, which I will round to 7.87. Okay. So that's how they got this confidence interval. Okay. So the interpretation of that is that we are 90% confident that the true population mean is in the interval between 5.8 and 7.87 hours. Because that interval includes the number 7, that is not strong evidence that the population mean is not 7. Most of the time, I use either the p-value approach or the critical value approach. I don't usually use the confidence interval approach, although this is good practice for confidence intervals. All right, next example. Data set 3, body temperatures in Appendix B. I think that can be found on a website somewhere, but I don't think we need it right now. Includes measured body temperatures with these statistics for 12 a.m. on day 2. N equals 106, so the sample size is 106. X bar is 98.2 degrees Fahrenheit, and the sample standard deviation is 0.62 degrees Fahrenheit. Use a 0.05 significance level to test the common belief that the population mean is 98.6 degrees. So I think this example is going to be a little different in a couple of ways. First of all, the sample is a simple random sample. Second of all, the sample size is bigger than 106. So regardless of the distribution of the original population, this sampling distribution will be normal. Okay, so the first step, the claim that the population mean is 98.6 degrees becomes mu equals 98.6. The opposite of that is that mu does not equal 98.6. So here are the two things that are different about this example. Number one, the original claim is the null hypothesis. That hasn't happened before in any of our examples. And number two, the alternative hypothesis is mu does not equal 98.6. That's going to make this what's called a two-tailed test. All right, so as specified in the statement of the problem, the significance level is alpha equals 0.05. And because the claim is made about the population mean, X bar is the relevant sample statistic, and we're going to use the t-distribution because the population standard deviation is not known. So when we use our formula for the test statistic, we get 98.2 minus 98.6 divided by 0.62 over the square root of 106. And I'm hoping that as you're watching these videos, you're putting these things in the calculator and not just taking my word for it. The t-value comes out to negative 6.64. So this is a two-tailed test. Technologies use unrounded values to provide a negative 6.61. Well, that really doesn't matter too much. So let's see. The p-value, the exact p-value, they got 0.00. So why don't we hop back over to StatTrek. So I'm going to change the degrees of freedom to 105. And my t-score, I'm going to use the one we got out of the formula, negative 6.64. And now I need to erase this or the website will complain. Okay, there it is, 0.0000. It's not exactly 0, but that's what it rounds to 4 decimal places. And if you use the table, let's see, well, there is no row for 105 degrees of freedom. So if we just went with 100, because that's pretty close, 6.64 is greater than the largest t-value that's listed here. So I would like to draw another picture that explains what's going on here. Before I do that though, let me just make sure I remember. Okay, 2.626 corresponds to, well, let's use area in two tails this time. 2.626. Okay. So if I draw my t-distribution, what that's saying is that the combined area to the right of 2.626 and to the left of negative 2.626 is 0.01. Our calculated test statistic was negative 6.64. So if we plot negative 6.64 over here and 6.64 up here, all right, our p-value, let me switch to a different color here, is going to be this area right here along with this, those two areas combined. So that means that our p-value is less than 0.01. And because 0.01 is less than the significance level 0.05, that means we have a low p-value. And when p is low, the null must go. This means we're going to reject the null hypothesis. Okay, so now switching back over to here. Okay. I'm going to skip the confidence interval approach for this problem, but I will talk about the critical value approach. So again, the meaning of the critical values in this problem would be this. So because it's a two-tailed test, we are looking for a pair of t-scores that cut off a combined area of 0.05. Okay. So I can get that out of the table. Switch back to the table here. Okay. So area in two tails, 0.05. I'm going to use 100 degrees of freedom, 1.984. 1.984 gives me area in two tails, combined area 0.05. Okay. Oops, forgot to switch back to my okay, there we go. Sorry about that. I forgot to switch. Okay, and again, we've already calculated the test statistic. The test statistic was negative 6.64. That is well within the critical region. So that would give us the same conclusion. We would reject the null hypothesis. I have never done so much switching back and forth in one video before. Okay, and let's skip the confidence interval approach this time. All three approaches lead to the same conclusion that we should reject the null hypothesis. The p-value, which is very close to 0, is less than the significance level of 0.05. The test statistic t negative 6.64 falls in the critical region bounded by plus or minus, they got 1.983. That's probably a little bit more accurate than the one I got. And there's the confidence interval conclusion. Now remember that your conclusion is supposed to address the original claim. In this problem, the original claim was that the mean body temperature is 98.6 degrees. Since we have rejected that claim, the way that we're going to word our conclusion is there is sufficient evidence to warrant rejection of the common belief that the population mean is 98.6 degrees.